Hi, it's Mr. T here. In this video, I'm going to go over the solubility constant Ks. First, we're going to talk a wee bit about why it's important to learn about the Ks, and then I'm going to go through how it's derived and how we might do some calculations with it. This concept is under the general heading of equilibrium principles in aqueous systems, and this is a topic at level 3 NCEA. Okay, so here the first thing we need to think about is that whenever we have a body of water, and in this case here's a picture of a lake, the lake usually has a selection of ions that is dissolved in it. We have ions like sodium and chloride that have come from salt that has been worn away from rocks, calcium that's come from limestone that's come from rocks, and we have a little bit of magnesium and some hydroxide and hydronium ions that have come about from the equilibrium of water. At times, well, this would be pure water and that would be great, we would be able to drink this, but in many occasions the water in our lakes and rivers get polluted by, most of the pollution is by metals. They're called heavy metals. They're metals with larger molar masses. Examples are lead ions, chromate ions, zinc ions, nickel ions. Now these ions get into the waterways from various processes, mostly from human activities. So one of the human activities, let's have a look at one, is lithium-ion batteries. So lithium-ion batteries, what are they used for? Well, if you have a cell phone, your cell phone will be run by a lithium-ion battery. So here's if we take the back off an iPhone, we can see the lithium-ion battery just in here, and the lithium-ion battery produces the power for the battery. Also, if you have an electric car or have driven an electric car is an array of thousands of lithium-ion batteries. They're at the bottom of the car and they provide the energy for the power source. Now, lithium-ion batteries, electric cars, phones, these are supposed to be new technology, they're green technology. This is all true, but the production, the recycling, and the disposal of these can cause pollution in our waterways. Now, I'm not saying that this is the only way that we get pollution. Everything that we have in our modern life is produced from some industrial process, and there is possible pollution associated with that. But I'm just looking at this as an example. So there are three parts where the pollution might get into our waterways. We've got the production, recycling, and disposal. So in the production, we've got some major components of a lithium-ion battery are the lithium. We have copper that's used for wiring. You have aluminium that's used for parts of the casing. We have important for the actual working of the battery is cobalt, and we also have some nickel in there as well. So lithium, nickel, and cobalt, the major working parts of the battery, and then we have copper and aluminium supporting. Now here is a picture of a facility where they are taking the rock that contains the metal cobalt and they are refining it to get it into the pure form of cobalt. Now notice on the bottom right there are big ponds there. These ponds are used to hold the waste that comes off when the production process is happening. Now, the water in those ponds needs to be monitored. If the water from those ponds was let to flow directly into our river systems or into our lakes, it would cause pollution. There would be cobalt ions, there would be mercury ions, there would be lead ions, there would be other heavy metals that are in the same rock that the cobalt was in that are left in the water after the refining process. If I was collecting the lithium, so the next picture here is a picture of a plant that is basically what they do is they take water, salt water or briny water, water that used to be a sea has got more concentrated, and they evaporate the water off to make a concentrated salts of lithium. In that process, the water also concentrates lots of other salts and makes them a high concentration, and in a concentration that might be dangerous to the environment and humans. So also this water that's being produced needs to be looked after. Okay, so we can see that the production of these batteries can cause some potential for some pollution of water. We also have a problem with recycling. Now, the problem we have with recycling is we have some prototype recycling factories, but the batteries aren't recycled very well. So of the actual metals that are found in the batteries, only really the aluminium and the copper that's used mostly in the casing and the wiring can be recycled easily. The rest of the heavy metals, the cobalt, the nickel, and the copper, sorry, not the copper, the cobalt and the nickel, and lithium, they are just crushed up and put into this fine sort of slurry and waiting for a better process to recycle them. Now, where do we store that? Where do we put that stuff that we're not using in the recycling? We know that cobalt and nickel can be dangerous chemicals. We need to look after where we put them. Well, usually what happens is when we dispose of the batteries, if we're not recycling, or sometimes the parts that we can't recycle, we put them into a landfill. Now, here is an example of a landfill. This is actually one in Timaru in New Zealand. Notice that the landfill sits adjacent, right next to a river, and the river is about to flow into the sea. Now, so the potential here is that these metals that are in these batteries, and from many other things that are disposed, may leak or leach into the water that's beside it. Now, and this might be washed out to sea. The issue that, well, the problem that we have here for chemists is, okay, so what if this happens? Is there a way to monitor this? Or even more, is there a way to work out that we could get rid of dangerous ions that are in solution once we know that they're there? And actually there is. And the start of this process is learning about the equilibrium of ions in water. That is, how do ions get into water? What concentration of ions can a certain amount of water hold? And what concentration of what type? And once we know that, we can then work out how we might remove these ions from water. And the first step along the way to that is to finding out about the equilibrium constant, or Ks. And that's what we're going to look at in this video. So, what is the Ks? Well, first you have to know that there's something called a sparingly soluble solid. Now, a sparingly soluble solid is a solid that if you dissolved it in water, you would have some of it dissolve into water. So here I've got silver chromate. Some of it will dissolve into water. And then what will happen is some of the ions that are in the water will start to dissolve, will start to precipitate back out. So a sparingly soluble solid is one where only a small amount of the solid will break apart, dissociate, dissolve in the water, and then the ions that have broken apart will actually come back together and form the solid back again. So in total, only a very small amount of, in this case, the silver and the chromate ions are going to be found in the aqueous or the water solution. Now we draw an equation for this, and our equation looks like this. Our equation is the silver chromate breaks apart, goes to the silver, 2 silver ions plus a chromate ion, and notice it's at equilibrium. So that it's got a special type of arrow, one that goes forwards and backwards. And what that depicts, it depicts both the forwards reaction, the number 1 reaction, and the backwards reaction happening at the same time. This reaction is said to be at dynamic equilibrium. Both the number 1 reaction and the number 2 reaction are happening at the same rate, and therefore it's at dynamic equilibrium. Okay, so what is a Ks expression? If I take this equation at dynamic equilibrium, so I've redrawn it again, and I've shown that it's interacting with the water and it's breaking apart. So what we can use is we can use the equilibrium constant equations. So here's an example on the right of the type of how we manipulate this equation to make it an equilibrium constant equation. That is, we take the products and we put their concentrations, we write them in square brackets, with their coefficient, the number in front of them, placed as an exponent. We put the products on the top, and we put the reactants at the bottom. So I transform the above equation to look like this. Now, so happens in this case, this is called a K expression, but if I want to make a Ks expression, I have to recognize two things. The first thing is that the concentration of the water in a sparingly soluble solution, that is, how much water there is in 1 litre, stays almost constant at 55 moles or 55.5 moles in every litre. That doesn't change. So because the concentration of the water doesn't change, I'm going to remove it from this expression. The other thing is the concentration of the solid, so how much solid is in the solid, that doesn't change either. So that's also going to be removed from the equation. Once I remove those two reactants, the two concentrations on the bottom, I'm left with a simplified equation. And this is it. This is called my Ks equation, or the Ks expression, sorry. Notice that we've only put the products in the Ks expression. We don't include the solid and we don't include the water. Also notice that the two silver ions that are in the original equation at the top here, the coefficient 2 has now been placed as an exponential. Also notice that the ions here have a square brackets around them. That denotes it's the concentration of those ions. So now we've learnt so far that we've looked at how to write an equilibrium equation and the equilibrium expression. This is a Ks expression here. So this is the original solubility equation, and now here's the expression. Okay, just before we go, we'll go over a couple of quick calculations. Number 1, how do we calculate the Ks if we know the solubility? Now the solubility is someone has measured exactly how much of the particular type of solid will dissolve in the water when we place the solid in the water. Okay, so the solubility for silver chloride is 1.7 times 10 to the negative 5 moles per litre. That's 17 micromoles per litre. That's not very much. It's going to be just a wee pinch of it will dissolve in 1 litre. Here's my my equation. So this is where we take the equation. We're going to draw an expression, but we're going to do some algebra. Now think about this. If the silver chloride is going to dissolve or separate into silver ions and chloride ions, you can see that for every 1 silver chloride that is dissolved, we get 1 silver ion. For every 1 silver chloride, we get 1 chloride ion. So the concentration of silver chloride that dissolves is equal to the concentration of silver ions that are apparent afterwards. And it also equals the concentration of the chloride ions. So if we if we say that the solubility of silver chloride is S, right? So if this equals S, then the concentration of silver ions must also equal S. If we say the solubility of AgCl equals S, then the solubility of Cl minus equals S. Now, the reason we're going to say that these two things equal the solubility, which they do, is so we can do a wee bit of algebra, because we're going to draw the Ks expression for this. Here it is. So the Ks for this equation is the concentration of the silver ions times the concentration of the chloride ions. But we've seen that the concentration of the silver ion is the same as the solubility S. So we're going to substitute that into where the silver ion concentration is. We've seen the concentration of the chloride ion is S, so we're going to substitute that in. So we do that and we get the following expression. Ks equals S times S, which, if we know our algebra, we can simplify into Ks equals S squared. This is an important equation. We use this anytime that a sparingly soluble solid or an ionic compound dissolves in water and produces a 1-to-1 ratio of ions. We're going to get this expression to work out. I can now, if I know the solubility, work out the Ks. And I do know the solubility. It's up here, 1.7 times 10 to the negative 5. So I can calculate the solubility for this. You can pause the video at the moment and you can have a go at calculating this solubility now. Right, hope you've unpaused the video. Let's see if we can work this out. So what we're going to do here is we're going to substitute this value into the Ks. So Ks now equals 1.7 times 10 to the negative 5 squared, and we're going to place that into our calculator and solve, and the answer is 2.89 times 10 to the negative 10 moles per litre. Now you might wonder, well, what does this Ks value mean? It's something we're going to use later when we're going to solve problems about how we might reduce the concentration of ions we don't want in a solution, or how we might calculate whether what concentration the ions in a solution have to be before they will precipitate or fall out of the solution. So this is the Ks for a sparingly soluble salt or solid that is a 1-to-1 ratio. See, that's silver to chloride, 1-to-1. So just before we go, we'll look at one that's a 2-to-1 ratio. So here, these ions are at 2-to-1. Notice the silver chromate has 2 silver ions for every 1 chromate ion. Now that makes this a wee bit different, because if I know the solubility of silver chromate, I can see that there's twice as many silver ions as the silver chromate ions that dissolved. So if the silver chromate equals S, the solubility, the silver ions equal 2S. If the silver chromate equals S solubility, the chromate ions equal S. So I can place that down here. So notice that algebra is going to be a wee bit different this time. I'm now going to write my Ks expression, remembering I don't put the solid in. I'm only going to put the ions on the right hand side in my equation. And the coefficient is going to become an exponent at the top of the square brackets. So we get Ks equals Ag square bracket squared times chromate square bracket. This is my Ks expression. Now for the algebra, I'm going to substitute the 2 times S inside the bracket here where we have the Ag. So what we're going to do is we're going to get this 2S bracket squared times solubility. Now 2S squared is the same as saying 2S times 2S, which ends up being 4S squared. And then when we multiply that by the solubility again, it becomes 4S cubed. So this is the Ks, this is a simplified Ks equation we can use to solve a problem if we know the solubility, but we want to find out the Ks for a sparingly soluble solid that is a 2-to-1 ratio or a 1-to-2 ratio. So if you again pause the video, see if you can solve what the Ks for this problem is. Okay, so substitute into the equation. So we get Ks equals 4 times 6.54 times 10 to negative 5 to the cube to the power of 3. We solve and we get the answer of 1.12 times 10 to the negative 12. Now, I've kind of got a wee unit sitting there, but we usually don't write the units for the KSs because the units change. So we can just either leave them out, or if you're interested in working out what the units are, you can go and search up a video how to work out the units of KSs. Righto, so in this video, we've looked about why we want to learn about water chemistry, or the chemistry of what happens in our water systems. And we're looking at it from a perspective is we often do things as humans that alter the number of ions that are in the water around us. And we want to look to how we can get the ions back to a situation where we have clean, safe water. The first step to being able to do that is to find out something about how things dissolve in water, and this concept of we have something called a solubility constant, and we're going to be able to use this constant in subsequent videos to be able to solve problems about the concentration of different ions in solution. I hope this video has been helpful. If you do find it helpful, please just make sure that you subscribe so you can look at the next videos I have, like it, and look out for the next video. In the next video, I'm going to go over some calculations on how we might find our KS if we know our solubility, and then further on, I'm going to go into how we might solve more complex problems. Thank you, and I'll see you later.